I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for these students, and you just ask that you bless this time we have together, Lord. In your name I pray. Amen. 9931. So, I said there were 4 examples that I want you to be able to parameterize. You shouldn't be surprised when I ask you to parameterize these examples. What were the examples? Circle, hyperbola, line or line segment, right? And also graph. So I talked about the first 3 last time. Let me talk about graph to complete that discussion. So what's a graph? The graph of a function, it's the set x comma f of x such that x is in the domain of f, right? This is a graph. So if I want to parameterize a graph, right, well, it's kind of silly. We can use x equals to t and y equals to f of t for t in the domain of f. This will be a parameterization of a graph. In other words, we can use the x-coordinate as the parameter for a graph. Now, so what I wrote down, and I'll soon box in red, these would be the scalar, here you go, this is the scalar parametric equations. For the curve. Let me call the curve C. But we could also write a vector, a so-called vector parameterization for C. A vector, the vector parameterization for C looks like this. R is a mapping from the domain of F to C. All right, this C is a subset of R2, right? So the input of R is real numbers from the domain of the function. The output is the points on the curve, which we're parameterizing, the graph, right? And the definition for this R vector of t is equal to x of t, t, comma f of t. So I'll box that in green in just a second here. This is the vector parameterization of a graph. Marker's worthless. So given any vector parameterization of a curve, it's very simple to find the corresponding scalar parameterization of a curve. Right? This is just a question of packaging and like grouping of, information. Let me make sure you're on the same page with me. If I tell you R of t is equal to, let's say, t comma e to the t, and that's for t in the interval 0 to 1, can you tell me the scalar parametric equations for this curve? In other words, can you tell me what x is as a function of time and what is y as a function of time? This is x. This is y. The scalar parametric equations are just x equals to t and y equals to e to the t. That's it. Yeah.
What is R of t? Not like that.
That's the parameterization of the curve. To draw a picture of it, here's what's going on. So if we plug in 0, what's R of 0? 0, 1, right? What's R of a half? Yeah, e to the 1/2, which is what? That's, yeah, well, that's 1/2 e to the, what's the square root of e? E is about 3, so what's the square root of 3? About 1.7? So that's like here somewhere, I don't know, here-ish, right? What's R of 1? It's 1e, so over here, here's 1/2, here's 1. So it's like up here somewhere. Oh man, poor planning on my part, but so the point is that this is R of 0, this is R of 1/2, all right? And I'll do it in blue, but this right here is R of 1. Right? It's a vector from the origin that points out to where the curve is at time t, right? And then if we look at where this position vector is tracing out as time varies, that gives us the actual curve itself, right? So this brown thing I'm drawing right here is the actual curve, which we're parametrizing in this direction, right? And in this example, this is a graph, right? What's the graph that we're parametrizing here? Y equals e to the x with domain just 0 to 1, right? Now, physically, we could think of this as describing the motion of a particle, right? The particle is going from, the point 0, 1 at time 0 to the point 1 comma e at time 1, right? And so R of t is the position of the particle at time t. This is what we could think of, right? The scalar parametric equations give me the x position and the y position separately, taken one at a time, right? But you could use other things to parameterize a curve besides time. You could use like arc length, for example. If you imagine taking a circle, right, and laying a string along the circle, you could use as a parameter how far you'd gone along the string to parameterize the circle. This would be an arc length parameterization. Yeah.
How is that scalar parameterization if it's like vectors?
We can always go from a scalar to a vector or vice versa. The scalar parameterization is just the components of the vector parameterization, like taken separately. So each vector parameterization gives me two scalar equations. It gives me x is the first component, y is equal to the second component function of time. Those are the quote-unquote scalar parametric equations. If you give me a pair of scalarimetric equations, I just put those in a pair. That gives me the position, if you like, the vector parameterization. So let me add a little bit more to this. So if t represents time, then we have a few things. Number one, R of t, which you could write as, x of t, y of t. In other words, x and y are both functions of time. This is the position of a particle at time t. Number two, we could calculate dr dt. And what that would mean is we differentiate each component function as a function of, we differentiate the x component, we differentiate the y component one at a time. So the velocity, if you will, is just dx dt comma dy dt. Well, velocity of the particle at time t. You're like, wait a minute, you're saying we can differentiate parameterizations? And we can do that by just differentiating the components of the parameterization. Yes, that's what I'm saying. You're like, I reject this. In Calculus 1, I was taught that derivatives stem from a limiting process. You said nothing about limits. This can't possibly be legitimate. Well, if you'd like, I could I could back it up and reproduce this in terms of a limiting principle if you'd like, but let's not do that because then I will lose all of you, right? We could introduce the derivative of a parameterization by a limiting process, and after about a half hour of math, or 20 minutes, we would find that this is a theorem. But for you, as a practical matter, this is the definition of how we differentiate a vector-valued function of time. What did I just say? Vector-valued function of time. Does that terminology make sense? You give me a time, t, r vector outputs r of t. Input, parameter, output, point, or vector if you like to look at it that way, right? T is the input, r of t, output. In, out. Right, a function is a machine. You give it an input, it gives you an output. It's just that a parameterization, the input is the parameter, the output is a point. You've been taught about functions where the input is a number and the output is what? Another number, right? That's just the first kind of function. There's lots of functions which take one kind of input and give a completely different kind of output. This is a good example of that, the parameterization of a curve. All right. So that's velocity. What do you think's next? Yeah, so if we take, oh, by the way, we have a reserved letter for this, which is v at time t. So acceleration at time t is dv dt, which we could also write as d dt of dr dt, which you're like, please, more notation. That would make me happier. So yes, fine, there's another notation, d squared r dt squared, which is also denoted r prime prime of t. And you got me. Fine, I forgot. V is also denoted r prime of t, also true. Other notations. The prime notation continues on. Right? Anyway, getting to the point here, whatever your choice of notation is, it is going to be the second derivative of the x component and the second derivative of the y component. That's the acceleration. All right? Position is a vector. Velocity is a vector. Acceleration is a vector. Right? Yes, sir?
How is position a vector? How is this a scalar?
No, position is a pair of scalars. The x, like we can talk about position as a pair of scalar equations. The x equation, the y equation, right? But together, to tell me where the position is, I need both the x and the y. I need two pieces of information. That's a vector. So, I mean, here, position is a vector, yeah. You could also think of position as a point. I wouldn't disagree with that. I mean, it's either a point in the plane or it's a position vector from the origin. So the position vector goes from the origin of your coordinate system to the point where you're describing. Now, personally, I think of position vectors being anchored at the origin. Actually, that's kind of not just me. That's pretty much everybody. and also pretty much everybody thinks of velocity and acceleration not being attached to the origin. Where do we think about attaching velocity and acceleration? We actually think about attaching them to where the particle is. So if I draw a picture of a path, something like this, all right, then we can picture the position, the velocity, the acceleration in each case. So the position vector is something like this. The velocity at the moment is ambiguous because I haven't told you which direction this path is going, right? Would you guys want to go left or right? Let's go right, fine. That figures. Let's see here. Just give a liberty audience, left or right. You know what they're going to choose. All right, so sorry, it's horrible. So the velocity points like this. At that point, anyway, right? The velocity points tangent to the curve, right? And then what? Acceleration is a little bit trickier, but acceleration points, well, that depends on the details, but it's probably for this one something like this. I don't know. So the acceleration actually has two parts. It's got a tangential part and a centripetal or a normal part. So it's got a center-seeking part and a tangential part, right? If this curve had constant speed, all right, so if the acceleration was purely just about changing the direction of the velocity vector, then the acceleration would be pointing towards the center of the osculating circle, which would be like this. But generally speaking, there can be a part of the acceleration which accounts for the particle speeding up as it goes along the curve. Now, I've been using this word speed as if you know what it is. What is speed? Speed is not equal to velocity, no? Speed is the scalar of velocity. That is close to the truth. Speed is a scalar associated with velocity, true. Anybody care to refine that more? So here's some notation. It's the magnitude of the velocity. Speed is the length of the velocity vector. Specifically, speed is the square root of dx dt squared. Did somebody say that already and I didn't hear you? Very likely. So speed is the length of the velocity vector. Yeah.
Will the velocity vector always be the tangential line?
Yeah, velocity is always tangent to the curve. Unless we're talking about nonstop curves, right? So like if the curve came to a stop, then this all kind of falls apart, right? That's kind of the annoying thing, right? If you're talking about the motion of something that does like this, it's like I'm gonna wait a day, and then I'm gonna jump over to here and wait a day, and then I'm gonna jump over here and then wait a day. Calculus doesn't do so well with this problem, right? You probably need to think about other mathematics beyond just calculus for that. Or you got to break it into pieces and treat each piece separately and then look at the sum total of what's going on. So there you go. Position, velocity, acceleration. What's the derivative of the acceleration? The jerk. That's right, yes. So we don't talk about this too much, but the jerk as a function of time is d a dt. All right, so here's physics 231. F equals to ma, where m is mass and F is net force. And the definition of the acceleration is the second derivative of the position vector. So now we've covered physics 231. Are you happy? I'm just kidding. There's also this other thing, right? What's that other thing? This was very controversial last semester. I taught physics 201, and I did something that was really a little bit out there. I talked about this thing called the third dimension. Some of you are experiencing it right now, right? There's like a third dimension. We can go this way, we can go that way, but hey, we can also go up and down. And that's missing from this discussion, right? And I'm not going to put it in. That's calculus 3, right? What's that? It's 30% more confusing? No? No. But anyway, for us, we'll just look at two component vectors in here, all right? That's all we need to describe curves in the plane. So if I give you position as a function of time, can you find the velocity, acceleration, and speed? I hope you can, all right? We can prove that the speed is actually also equal to ds dt, where s is arc length. Now, I'll spend some time delving into this idea more deeply in future lectures, but I should mention, at least right now, that if we wanted to calculate the arc length, we could just integrate the speed over time. By the way, we'll spend more time in a future lecture, but let me just put this marker down. The arc length for a curve is the integral from, say, t1 to t2 of the magnitude, well, ds dt dt. But of course, that actually means integral from t1 to t2 of the square root of dx dt squared plus dy dt squared now. Now, I should explain why that's actually true in a little bit more depth, but not today. But this is one of the things we can do with speed. We could integrate the speed over time. That would give us the arc length. Right? So here, T1 and T2 are what? The domain of the parameterization, right? T1 less than or equal to T less than or equal to T2. Let's look at an example. I'll give us the velocity as a function of time. Let's say it's equal to 3 plus e to the minus t, and then t sine of t squared. Suppose we're given this velocity. And let's suppose we're also given an initial position. What do you guys want to make the initial position? Any ideas? 0, 0 is the initial position? Well, all right, fine. I guess I asked the question. I left myself open to it. So you want to put it at the origin at time 0. Not an especially exciting choice, but I'll allow it. Also given. What's the question? My question is to find r of t, a of t, and the speed at time t. You should feel a sense of relief washing over yourself, right? That annoying creative aspect of the parameterization discussion is gone, right? I'm giving you a thing. There's formulas. You're applying the formulas. You're calculating something, right? It's not so overwhelming, is it? I know, if you're feeling overwhelmed with the parameterization discussion, you're not alone. It is a difficult concept when you first see it. And I'm going to try to give you guys a lot more problems to work on it soon, all right? I would remind you, you can read the notes. I have a bunch more examples there already, if you haven't already. I think chapter 12 or 13 there. Okay, so here we go. So what would the acceleration be? That's the easiest one. Let's do that to start with. Acceleration's dv dt, which is what? We differentiate 3 plus e to the minus t, right? And then we differentiate t sine of t squared. What do we get? Well, derivative of 3, otherwise known as 0. Derivative of e to the minus t is minus e to the minus t. This is the derivative of a product of functions of time. I would remind you we need to use the product rule. So this gives us the sine of t squared plus 2t squared cosine of t squared. Because the derivative of sine of t squared is cosine of t squared times 2t, but 2t times t is 2t squared. So there it is. That's the acceleration as a function of time. If the net mass in this problem was 1, say 1 kilogram, and suppose this is in meters and seconds, what you're looking at right now is the net force, right? Apparently a really wacky force would be necessary to achieve this trajectory through space, right? Ah, another word. R of t is also sometimes called the trajectory. Although I think the word trajectory is sometimes more associated with the locus of all points which the path, the position vector traces out. Yeah? If I thought about trajectory, maybe I'd think about that. That's the trajectory as a function of time. Okay, anyway. How about position? Remember, v is dr dt, right? So to find the position from the velocity, what would we have to do? Right. I heard integrate. So position should be equal to the integral of v of t dt. Yeah? And so that is the integral of 3 plus e to the minus t dt, comma, integral of t sine of t squared dt. I don't know if you noticed or not, I just made a definition. This is the definition of the integral of a vector valued function of time. We integrate the x component and the y component separately, just like this, all right? Again, if you look at my notes, I have defined these integrals as mathematicians do, you know, with like a little box and all of the trappings, and I could write that out on the board, but I think you guys understand. Integral of the vector we integrate. So what would the integral of the x component be? Looks like 3t minus e to the minus t plus, let's say, constant 1. What's the integral of the second one? This is a u equals t squared substitution, right? So I believe if we do 1/2, or rather minus 1/2 cosine of t squared plus c2, that's the integral of the second component, making a u equals t squared substitution. Now, believe me, don't believe me, differentiate my y component. Does it work? If we differentiate cosine of t squared, we get minus sine of t squared times 2t. The 2 cancels with a half, the minus cancels with the minus, and I'm left back with t sine t squared. As you can see, my integration is legit. Although me using that word, maybe not. Let's see here. I don't know if I have the life experience. Some of you might say I'm too legit to quit, but that's probably before your time. I'm sorry, I must stop. What's r of 0? We got what? 3, what's e to the 0? Actually, what's 3 times 0?
0.
Yeah, so maybe 0. 0 minus 1 would be better, plus c1. And how about my other component? I've got, what's cosine of 0? I need to go get my calculator to punch it in. Is incorrect. At this point, you should know cosine of 0 is 1, right? So that is, there's a minus a half out here though, right? So that's minus 1/2 plus c2, yeah? And because you guys put it on me, that's equal to 0, 0. That was the initial position. So this tells us that c1 is what? c1 is equal to 1. And apparently c2 is 1/2. And in the interest of not hurting your backs in the back and or neck, we've just arrived that the position as a function of time is 3t minus e to the minus t. c1 was what? 1 plus 1. And then minus 1/2 cosine t squared. And my c2 was plus 1/2. There you go. That is the position as a function of time. All right? And what was the other question I asked? Speed, right? So can you guys tell me what the speed is here? Speed, the magnitude of the velocity, it's the square root of minus e to the minus t squared, right? Plus, what was my y velocity? What's dy dt? Sine t squared plus 2t squared cosine t squared. Yowzers. That squared. This is the length of the velocity vector. The square root of the sums of the squares of its x and y components respective, yeah. Oh, have I done that? Oh, man. Oh, yeah, this is... that was so exciting, too. But no, you're right. Yeah, I should actually... This is the danger of... I'm too close to the board. Yeah, you know, by the way, what's the magnitude of the acceleration? The answer to that question is something that you'll have to think about for certain Physics 231 problems. Let's see here. But that's pretty much it. So 3 plus e to the minus t. And if I could just... I need to get... Oh, I did bring glasses. I should actually wear them. T sine t squared. So there you go. That would be the speed at time t for my example. Listen, if you wanted to calculate the arc length as a function of time, since we've done all this work already, let me just tell you here. Arc length as function of time t based at t equals to 0 would be s of t is integral from 0 to t. And then what you got to do is replace your t with some other integration variable, typically a tau. So like e to the minus tau quantity squared plus tau sine of tau squared d tau. this gives you the arc length as a function of time t. I haven't defined that formally, but there it is. If you integrate the speed from, say, a base time to time t, that gives you the arc length as a function of time. I claimed that the derivative of the arc length function with respect to time is speed. Can you see why that would be consistent with what I wrote on the board? My claim is that dSdt is equal to v, where that's the magnitude of the velocity. What is this here? This is nothing more than the velocity at time tau. What happens when you differentiate an integral with a variable upper bound? What's FTC1 say? Fundamental Theorem of Calculus Part 1 told us if we differentiate an integral with a variable bound, right, then we just get the integrand back again evaluated at the bound. In other words, we get dSdt equals to the speed. So this is, you know, you're like, what's tau? Tau is a dummy variable of integration. Here we're using t as a fixed but arbitrary time. I shut up. So if you can understand this example, you're doing pretty well. This is a lot of what's tested in terms of just, calculus of paths. And where it's important to us in Physics 231, understanding the relation between velocity, position, and acceleration. It's just integration and differentiating, but not one function, two at a time, where they're paired as a vector, all right? Now, I have assigned you some other problems in the homework about triangles and stuff, and I'd like to come back to that at this point. So let me do that. So I told you guys last time that we can take a vector and we can think about it as what? Magnitude and direction, right? We can talk about the standard angle for a vector. Remember that? So last time I mentioned to you guys, if we have a vector v like this, we can write it, of course, as v1, v2. That can be repackaged as v times v hat, where v hat is equal to, we figured it out, cosine theta, sine theta, and theta is the standard angle for the vector. Let me be more specific here. If I had, I don't know, this vector out here, which said had the vector, let's say, how's it go? Square root of 3, 1, will that do it? Sorry, I'm thinking. That's not what I want. Well, let's just deal with it. We'll deal with that one. So what's the, if this is my vector, what's the magnitude of the vector? Am I thinking about v being velocity at the moment? Not really, right? This is just a vector. Okay, so context matters here. You could use w if you don't like v here, all right? Anyway, so what's the length of v? Yeah, square root of 3 squared plus 1 squared, also known as square root of 4. And I think somebody told me 2 like a few seconds ago, right? So the length of that vector is 2. So the magnitude is 2. And so what do we have? We have cosine of theta. So this distance here is the square root of 3. This distance is 1. The hypotenuse has length 2. So cosine theta is what? It's square root of 3 over 2, yeah? Sine theta is what? 1/2 in this case. Can you guys tell me what theta is? Theta is pi over 6. It's 30 degrees. So that's the standard angle for this vector, which I'll make red here in a second. All right. Okay, so next step in this discussion is you might wonder, given two vectors, say vector A, next question, two vectors A and B like this, right? Suppose you have two vectors in the plane. What's the angle between them? What's the angle between a given pair of vectors? And I'm not saying that that's the standard angle. I'm not even supposing that B is horizontal, right? Now, you guys are probably pretty good at trigonometry. You got here after all, right? That means you've passed Calculus 1. You have some experience with these things. So you probably could figure that out, right? By just looking at right triangle trigonometry and suffering through it. If I actually give you numbers for A and B. But what I want to show you is there is a vastly simpler way of thinking about it in terms of something called the dot product. So here's the definition. A dot B is equal to A, B, well, this is not the definition, excuse me. A is equal to A1, B1 plus A2, B2. All right? And a theorem says that that's equal to AB cosine theta. So this is definition. This is a theorem, a derived result, where A is equal to A1, A2, and B is equal to B1, B2. Yeah. This is the dot product of A and B. Good question. It's also sometimes called the scalar product because the dot product is a number. All right? What this number represents is, depending on how you want to look at it, either, well, let's say it this way. The bigger the dot product is, the more in line A and B are. So if A and B are straight up parallel, if they're pointing in the same direction, the dot product is just the product of the magnitudes of the vectors. Right? If the two vectors are antiparallel, if one's pointing in one direction, the other's pointing exactly the opposite direction, that's the largest negative that the dot product can be. So it'd be like minus the product of the magnitude squares if they're going in opposite directions. If the vectors are perpendicular, then the dot product is 0. So dot product being 0 gives us a way of detecting when two vectors are perpendicular. Yes, sir?
What is A1 and B1 and like A2 and B2 and like?
These are numbers, the component.
How are A vector A and vector B? How are those numbers like?
A1, A2, B1, B2, all numbers. Right?
They like,
for the moment anyway.
are they like points on the line or on the?
So for example, this could be A. Let's say that's 4, 1. And B might be over here somewhere. I don't know. B would be minus 4, make that 4, 2. B would be like minus 4, 1. Oh, and let's see, I messed it up. This is maybe 7, 2, right? There, something like that. Yeah.
The third part of this, the definition there is A cosine. How do you
Here,
apply the
A is the square root of A1 squared plus A2 squared. Good question. B is equal to the square root of B1 squared plus B2 squared. So this is the typical physics 231 notation. It's a good notation. We use the symbol with the vector for the vector, the symbol with a hat for the unit vector in the direction of the vector. The symbol without the vector, just the letter, is the magnitude. So in this notation, we always have this, like A vector is A times A hat etc. So A is the magnitude, A hat is the direction. Any vector can be written as a magnitude times the direction. Yes, sir?
What exactly does the hat denote?
Unit vector in the direction of A. So depending on your system of units, this is a hat you don't want to wear, right? I mean, if you're working in feet, like if you wear this hat, it makes you a foot tall. I don't know. I guess that could be bad. Maybe you want to be small, though. I mean, being like a foot tall would have its advantages, right? I mean, I don't know. Yep.
So is the dot product, like, if you multiply two vectors, then it gives you the vector, like, in between them, or?
No, it gives you a number which somehow specifies the degree to which they're parallel. And also, it tells you other things. Like if the dot product is 0, it tells you that they're perpendicular. But the dot product of two vectors is a number. Let's do this one. So A dot B is what? So minus 4 times 7 plus 1 times 2. That's what? Minus 28 plus 2 equals minus 26. So the fact that that's negative tells me that they're kind of pointing in opposite directions. Right? The angle between them is more than 90 degrees. They're obtuse. Right? They're not acute, the angle between them. And to figure out that angle, if you believe my theorem, what's the magnitude of A here? Square root of 49 plus 4, right? Square root of 53. What's the magnitude of B? Square root of 16 plus 1, square root of 17. So if you, that theorem I wrote down there is equivalent to the law of cosines. To prove that formula, if you had the law of cosines in hand, you could derive the formula, and vice versa. That theorem is non-trivial. It is a deep geometric comment relating the angle between the vectors and the components, the magnitudes. It's a precious and wonderful formula. We should use it wisely. Anyway, so minus 26 is allegedly equal to the square root of 53 times the square root of 17 times the cosine of the angle between them, which I don't know. I mean, I can see it, but I don't know what it is. But now, with a dot product and this little theorem, I can straight calculate it without a protractor, right? Without breaking things into standard reference angles or any of that stuff. Just directly calculate the angle. What is it? So theta is inverse cosine of minus 26 over the square root of 53 times 17, which is, this sounds like a job for Google. Inverse cosine of minus 26 over the square root of 53 times 17. Didn't make it. We didn't make it. Grouping the 53 and 17, that was a step too far. Let's try that again. 53 times 17, 901. Square root of 901, not square 901, square root. Oh, now it's giving, what a square D air compressor. Wow, interesting. Square root of 901, come on, 30. Oh, I could have done that. Why did I use stupid Google for that? 30.01. Inverse cosine of minus 26 over 30. Come on. No, I don't need, you're stupid con. Goodness gracious. You know, this would all be fixed by now if I'd actually brought this thing called a calculator. It's in my office. Did you guys figure it out? Somebody tell me, please help me.
150.01.
150 point what?
How far do you want around it?
About 150 degrees, I'll take that. So, think about this. That problem I gave you to find the angles in the triangle, what you can do is take the points that you're given, right? Like P, the Q, the R, right? And if you think about vector A being q minus p, and if you think about vector B being r minus p, right? In other words, A is pq, B is pr, then you could find the angle, the interior angle, using this technology without doing any kind of picky trigonometry, right? You could just use this dot product to calculate interior angles between two vectors. It's a triangle too, so once you find two angles, what's the third? 180 minus the other two, right? But if you calculate it separately, it gives you a check on your work, does it not? So anyway, I shut up. So tomorrow, I will ask you if you have questions about the mission, and we'll try to spend some time talking about your homework, all right? Thanks, guys. Is this stuff making more sense? Okay.
I mean, like, say it was better, but like,
Like,
The-
once you have it in the XY components, the calculus with it is fine.
Right, but I agree, there's like this very uneasy, because you don't know where the edge of the parameterization discussion is, like, what are you expected, that's why I tried to say that these 4 examples is all I want you to know, because I know you need like guide rails for that part, because it's just kind of like, it goes on and on.
so when we did, like, when we made the equations for the parametric functions, like, do we have to know how to make those equations? Because you kind of just, like,
You have to know how to make the equations for like a circle, a hyperbola, a line, and a graph.